Hello, good morning, good afternoon, good evening, good night, wherever you are from any part of the world. Thanks for joining this webinar on SDS Prediction Gone Right. This is me, Lakshmi Narasimhan from MSys Technologies. I'm the solution architect here. Right, so this presentation, we are trying to showcase or understand where the SDS industry is actually going on. How does SDS help or has improved the situation in this industry? So as this technology, as we see it, there are a lot of marketing buzzwords around, and just sorry for the interruption. So as I see it, there are a lot of buzzwords around in this technology. So I thought it would be prudent at this point in time to understand the background about all these new technological initiatives that has come up. So these buzzwords are being thrown about in various fashions and all around the place, but without a clear understanding of what it is. So are these just marketing buzzwords, or is there a real technological backup to all these words that is helping us improve in our daily deployment and environments? So that is something I would wish to begin with. Then we will see the evolution that we have gone through, and we will see the evolution as I see is, as the storage industry by itself, how it has gone over this entire phase to where we are today. And we will have to understand the pain points of a customer, and to understand and appreciate what SDS is bringing to the table, and then see how SDS is going to help us and solve those problems. And then finally, appreciate, like, SDS is not just solving some of the problems, but also bringing in a new initiatives or directions to where this entire industry could expand to. And finally, the conclusion. Let's go on. So this is the cloud as I see it, right? So everybody understands, I've been talking about cloud, and there is a data center behind it, and there is also a term called software-defined data center. So this is how a typical data center is typically looking like. There will be rows and rows and rows of machines, compute and storage nodes attached, and then each of them is arranged over racks, and you will have to provide them power. So look at the scale of the growth that has gone in here. Right, it's not so to appreciate this phase, your storage stack, and not just storage stack, the entire stack that is supporting this data center, this environment has to scale, right? So there are three very critical components as I see it. One is the storage, the networking, and the compute. And we will have to see how we have gone there, and what was our humble beginning. So to understand that, how did we start? We had a typical direct attached systems, a single, chassis, and that chassis could house 2 or 4 drives maximum, and your applications were deployed on that. So you have a dedicated servers like this, and then your applications and environment grew, so you needed more storage, and therefore you try to expand, but your chassis has, run out of place, so you'll have to somehow see how you can expand your storage. Then the idea stuck that the storage silo by itself could be pulled out and maintained as a separate silo, and this connected to your main compute machine through a pipe, right? And there was dedicated storage protocols for that, to just connect your storage silo. And the foundations of the storage started with the SCSI. SCSI was the primitive storage protocol over which, even today SAN topology is built. So all the fiber channels and iSCSIs and SAS internally embed carrying SCSI packets. Right, so you have this dedicated silo that is holding storage, so it can scale on its own, and this by itself is actually started out again as just a bare storage repo that could be accessible across a network running over a proprietary storage protocol. Now this started out as a JBODs. If you understand what JBODs is, JBODs means it's just a bunch of disk. Your raw physical disk which was sitting inside your chassis as a 2 or 4 node drive has come out and is sitting in a separate storage silos, and you're accessing your compute machines is accessing those storage silos over a network. Now this is a dumb storage enhancements, right? So you expand your storage just by adding JBODs. But then we added more services to it because drives could fail. So there were smart controllers sitting in between your compute nodes and your storage, trying to understand and intercept all your requests and then push it into this JBODs, which is a bunch of drives. And this smart controllers now started giving more storage services. Herein came the first phase of virtualization as we understand. It's no longer your raw physical drive is directly mapped to your compute machines. This storage smart controller sitting in between created an illusion of providing a logical drives through administrator interface, where administrators could create various configurations for resiliency, redundancy, and various services like cloning, replication. And typically these smart controllers manage their drives through a RAID, which is one of the protocols for managing redundancy and to restore your recover your data in case of drive failures. So this smart controller sitting in between, that was the first enhancement happened to your storage silo. Storage silo is now not just a bunch of drives, but there are smart controllers in between sitting, understands how to manage data, how to place them, how to recover them in terms of failures, and on all these added features. Now, similar to how storage is accessed over a separate protocol. So I said there is a separate proprietary protocol. So all your compute nodes now need to have something called as a HBAs, host bus adapters, which would actually let your compute node talk to that storage over the network. So there is some protocol translation happening. So we already know that your drives were slow, but now you position those drives across the network just to ensure that you're scalable, you're recoverable, you could recover, you could do data recover, all kind of disaster recovery things. But speed wise, it is just still over the network, and you need to have every machine that is going to access the storage needs to have a dedicated host bus adapter that lets you access the storage protocol. And think about it, every machine is not just going to access your storage, it is also going to access networks. And networks, Ethernet started ruling roost, so that so every machine needs to have network. None of the applications are now, on your internal direct machines. It is over the network, hosted on the cloud. So typically, it has to have a network connection. And by network I mean, so your compute machines has to have one more adapter or card which will provide network connectivity across. Typically this is your Ethernet card attached to your compute machines. So you have two different cards serving two different paths, and one of them is going through a storage silo, the other one is going through your network silo, right? And you are trying to manage this in a large environment. So you have lots of compute machines, you have lots of network cards on them, and a separate storage silo and a separate network stack. By network stack, there will be routers and switches providing connectivity. And administrating people, who are administering this whole environment always need to firefight one over the other. So your storage is down, you improve your storage. Your network pipes are low, so you improve routing, switching pipes. Your adapters are separate, so you had only 10 gig, then 40 gig, and this was a never-ending task. One of the other. It's impossible for some administrator to just ensure that everything runs smooth. So this was typically how it was, and then came in the wave of converged infrastructure. I don't know how many people do understand, today we talk about hyper-converged infrastructure, but earlier to that there was convergent infrastructure, and you would appreciate now, having given this background as to what it is. Convergent infrastructure means your compute machine doesn't need two different paths to access a storage or a network. So they are two independent hardware cards, protocols, everything different from your compute machine to access them. One runs to a typical SCSI over proprietary protocol SAS or fiber channel or iSCSI. iSCSI is not one of it. So that is one. The other one is running your network stack, TCP, IP or Ethernet, right? So whatever it is your traditional network stack. So both of them now merged on to be supported on a single card. Like you can access your storage over Ethernet as well as you can reach out to the wider internet through your Ethernet network card. And that convergence is because of iSCSI. iSCSI brought in what was totally two different silos for the administrators to a single interface. So your whole infrastructure or your compute node only needs a single card, a network card through which it will be able to access both your storage as well as your network. So this convergence of two different protocols on a single card, ensuring your compute nodes is able to access two different storage as well as network from it, is what is converged infrastructure, right? So you have only one hardware component on your box and two different protocols are merged onto one. And iSCSI was the one. So like that basically carries again SCSI packets over internet, TCP or UDP, whatever it is, the native protocol. So that convergence started something else as well. So we understand right now what is converged infrastructure. So what is hyper-converged infrastructure? So we saw that you could bring your network as well as your storage onto one, and on top of that we could do virtualization as well. So we could do the network virtualization having overlay networks, and we could do storage virtualization, which was already there in some form or the other. But now what was missing was the compute virtualization. So if your infrastructure does support compute virtualization, which means virtual machines as that's prevalent today, and you could have overlay networks in your infrastructure, like you could create as many virtual networks on top of your physical network, and as well as a fluid storage environment, which means you can carve out any amount of virtual storage out of your physical storage, no matter whether it is a block or file, and make it provision it for applications. Then what you have is an hyper converged infrastructure. So it's a virtualization on top. You converge adapters, and virtualization doesn't just stop with compute, but does virtualization on storage as well as network. All this put together is what is an hyper converged infrastructure as we see today. But marketing doesn't stop there. There's a lot of hype around it, and we will get to that. Right, so this is what in general the buzzwords, and I hope you had a good background on all of those and how the industry evolved there. So the critical problem, as we see, you saw the first picture of a cloud data center. A cloud is just a metaphor where you can see like it's nebulous, like it's just fluid, it's flexible, it can grow in all scales. Now all those metaphors do apply here as well. I want to show you some of the numbers that we are looking at this to appreciate the scale of the problem. I mean, it is mind-boggling. The data growth for, let's say, this slide came from last year. So there will be even more information that's going to happen here. So some white paper from Data Core, I believe. There is a reference at the end of the slide as well for people interested to dig deeper. Here I would like to show you the scale of the growth in each of those domains. Medical imaging, you could think about your x-rays. It's those are growing at the rate of 500 terabytes per year. Genome sequencing, it's growing at 200% annual growth rate. You think about your personal photos, pictures by themselves. It's growing at 1000 petabytes plus, which is 100% compounded annual growth rate year over year, 100%. And these numbers, I mean, you could look at any of those, this one, squares there. All those numbers, you know, those the unit by itself is petabytes, and they are growing at a tremendous rate. And the whole growth rate story doesn't end there. We are looking at zettabytes per year. So we are already at 2016. Look at 2017 and 18. It's growing at 7.8 or 8.6 zettabytes per year. So that number. If you still can't appreciate, I'm going to give you some more numbers. So all this slides is to help you understand the scale in which the storage is going through. You know, the scale of growth. So the technologies that needs to support it, we are coming up. You know, none of the hardware existing protocols they are not going to stop just because we have a new way we are going on. The 40 gigabit fiber channel over Ethernet, you still have a market of 8%. 40 gigabit iSCSI, we still have a market of 14%. And 40 gigabytes NAS system, you still have 22% growth. All these the things are going to be there. But on top, you have something called as a software-defined storage that is growing at a mind-boggling rate of 28% as we see it, right? So what this means is we are looking at one side, storage is being grown at a rate of, you know, zettabytes. You know, those numbers are really huge. Think about your humble days, your first machine, probably you had some 20 gigabytes hard disk. Now we are looking at the scale of zettabytes. I know probably if you had time, you can work around how many number of zeros you're going to add to that. So given the kind of scores, so we are now scoping down to SDS to see, you know, I'm still showing you only market study done last year, 2015 by Data Core. The numbers and the poll they have done, I find it very relevant even this year and going forward. So I'm going to ask you again. See, these are some of the things that I will wish to share with you. What is the reason, right? What are the business drivers for really implementing SDN? Is it just all hype, or do you see, you know? So this was poll with people who wanted to evaluate or deploy SDN. So what was their story? All of them came up with, you know, three very specific reasons, you know, that's hovering around 45 to 52%. But given that it's all around the same range, you know, I think all these 3 points do stand to actually significantly point towards SDS. Extend the life of existing storage assets, avoid vendor lock-in and lower cost, and simplify management. Let's briefly think about what it is. Right, you have a cloud data center, you know, a typical data center. You're looking at probably thousands and thousands of nodes. Every node we are talking about, you know, thinking about number of drives, maybe 40, 80, whatever it is that it drives it support. Think about the expense that goes into actually, you know, putting up this infrastructure. And this infrastructure, what we are going to do today, you know, it's an initial capital expense that you're investing in today. Probably 12 months or 18 months down the line, the technology is not going to stop. Whatever you did install, deploy today is not the latest and greatest. But is just 12 months and 18 months your return on investment? Are we going to wipe up them all and then refresh them again? And keep in mind the growth that's happening to storage by itself. We're not talking about network pipes or compute. We're just talking about storage, one domain, one axis of the whole growth in a data center. And you're thinking to refresh every 18 months. No, I don't believe that's going to happen. So the whole story is, how are we going to control capital expense? That's primary goal. And especially true given the scale of growth we are looking at. So if you look at capital expense, the second thing is traditionally how do industries go and set up any deployment environment? They talk to some preferred vendors and get a quote. So everything would be from one particular vendor. So that's how industry typically tend to operate, right? So there is a great support happening from one particular vendor, and and you would be a preferred customer, and you know, and they would rush to solve any of your problems. But the whole problem here is, again, coming back to scale. There is no bargaining power if you stick to one particular vendor. The cost is going to shoot over the roof as well. And one more important aspect is, traditionally, right, how the industry is viewed at all these infrastructure pieces as, it never has to fail, right? And that is one more reason the expense of your hardware has gone very up. All your components, your network ports, your controllers, your hard disk, everything inclusive has to necessarily be redundant even at the lowest hardware level. Given that kind of a requirement, they want the physical hardware to remain stable in spite of failures. So there was a necessity for redundancy driven deep down into your hardware level, and therefore because of that the expense was very high. It turns out to be very expensive. So and on top of it, we are sticking out to particular preferred vendors. So the bargaining chip for controlling cost goes, it's not high. And we are looking at management. So if you're looking at these cloud scale of data centers, there's not going to be a single vendor who is going to do that. So supposing you have two or three, and look at the administration, how one could seamlessly manage this all these different vendors. So even if you really wanted to have multi-vendor systems, the administration of those things, provisioning was not easy enough. So all these three things, as I see it, you could independently say them, I prefer this over the other. I mean, all three needs to be solved, because the scale of the problem really pushes the envelope, and all these three are not three different things. I can choose. I want all three. So is SDS really helping me do that? So again, the next poll is, again, what are the primary reasons your organization chose to deploy storage virtualization software? Why? Why would an organization choose? So high availability, disaster recovery, cost reduction, we spoke about all that. I mean, some of them are really features that are supported in legacy storage controllers as well. But a couple of things do really add value here with SDS is adding capacity without disruption. Right, you don't want when you're moving, upgrading systems, you don't want any sort of discontinuity in business. It has to be up. Reliability, availability, serviceability. I don't know if you have heard of those terms. And your data center and every company that is actually pushing service out there is looking at what 99.99. I don't know how many nines after 99 you are supporting. It's a race out there. It's so your system, your infrastructure has to be available 365 days all through the year, right? It's that is a given, right? I mean, there is no take over it. So given that scale, adding capacity, it's going to grow. We already know the scale. I've given enough material to understand the scale of growth we are talking here. So storage has to grow. It has to be, there has to be a business continuity. Cost, we will have to somehow cut cost. But the whole thing is there has to be absolutely no downtime. That is very critical to understand. So those were some of the inputs that we got from people who are trying to evaluate or deploy last year, and they are still valid even today. To summarize, generally, at overview, what those problems are is capacity planning. If you have really thought about installing infrastructure for your company, the planning methods that we traditionally use, looking up and charting, is no longer valid. I mean, it's completely outdated. So capacity planning is one big issue. There is no way somebody can realistically estimate that, okay, this infrastructure is going to survive for the next 6 months. Administration is a nightmare. This is true even today. There is a separate SAN silo, there is a separate NAS silo, and if you understand those terms, SAN and NAS, SAN lets you access your storage over proprietary storage protocol. NAS is as a file level access over the network, and they started exporting file systems over network. Typically there is NFS and SMB protocols for accessing them over the network. So, but eventually NAS in turn, behind NAS there will be a SAN or a set of hard disks to actually manage data. So you had separate SAN and NAS, and there was complete chaos there trying to manage them. Reliability, availability, and serviceability. I've just touched about it. How many 9s after 99 are you supporting? I mean, this is insane today. And vendor lock-ins and preferred partners. That's how industry typically tend to operate. If you want to set up an infrastructure, you talk to your preferred vendor, and you're stuck with that vendor for your next, whatever period. And you have those companies, vendors, infrastructure sitting inside. So it's so whatever you prefer to grow, you are in a very hard place right now, between a rock and a hard place. And how hardware systems, I touched about this as well earlier. The intention was the design element has to support redundancy even at the hardware level. So the infrastructure cost was exorbitant even from the lowest level. And it has to support standard policies. I mean, there is no two ways about this. Replication, archival, disaster recovery is all there, but on top of that, we are looking at one different unique aspect of a data center. Replication by itself was totally controlled by these smart controllers in your storage, be it an NAS controller or a SAN controller. Right, so in data center, typically you have tons and tons of storage nodes in your data center, but not all of them, for purpose of redundancy, go under the same power line. A simple scenario I'm telling you. So if there is a power cut on one line, I mean, there is still, your application should see your data. So what this really translates to as a requirement is for your storage controller to be aware of the topology of your physical infrastructure. This is never a requirement for your SAN or a NAS controller. But given the scale, again, we are going at, this is how it's going to be. Your data center is going to have rows and rows and rows of racks and racks inside, having nodes. And your data, all of them, if you had 10 replicas for, just for this discussion, and all your 10 replicas went to different nodes in a rack, but the rack was in a single power line. So what's the point? Your replica is meaningless when the power goes off, right? I mean, that's a typical one use case. So there has to be more control for administrators to control how data can be placed in your network. So that is something that has to be supported going forward. So those are some of the plaguing problems that we saw. I mean, from earlier. So how is this hyper-converged systems and SDS coming in here? So Apol, again, so given the plaguing problems, how are you trying to address them? Are you currently evaluating hyper-converged systems? Last year again, there has been 21% of them saying yes. For what reason? I want to consolidate compute, networking, and storage. I can no longer fight independent silos. It's become a nightmare. So what's the way? I want hyper-converged infrastructure. Remember, hyper-converged infrastructure gets you all in one piece, and there is virtualization of compute, storage, and network. So SDS, SDN, and compute virtualization are components of it, right? And your typical software-defined data center means it is going to be sitting on top of these three basic tenets: your software-defined storage, software-defined network, and compute virtualization. Right, increased availability and simplify management. Again, one of the core areas. Administration is a nightmare, and performance. So people felt, deployment felt, when people are trying to move from there, given the kind of problems they are facing, I want some relief. They are looking at hyper-converged systems and SDS and stuff, and these three basic elements people are more concerned with. Let's see, about how the current trends do really address them. So in converged infrastructure and hyper-converged infrastructure, what does SDS do? So I told you earlier that that the hardware and all components on top has to be totally redundant. But it doesn't matter. Even with all that redundancy, you have seen failures. I mean, it's just a norm. Your complete metro city could go down. There could be a number of reasons, and even the typical human error could result in a data center outage. So there will always be reasons to failure, and it cannot be all avoided. So what is the other way? So other way, what does SDS bring in there? SDS says it doesn't matter. Use your most custom off the shelf components, right? You don't need your expensive toys sitting in your hardware. Nope. Just go get a plain vanilla server from the market. It could be labeled, doesn't not labeled, white label, doesn't matter. Get from any vendor. Make all this software solution and make it hardware agnostic, and this software stack should really work on this plural environment. So move from a preferred partner to embracing plurality where multiple vendors are supported. And placement, this is critical again. Your data placement strategies, it has to be amenable to your administrator's wish, your data center topology. So, and that's what your SDS is bringing into the picture. And what else? So we already talked about administration in terms of a failure. If there is a human intervention, it's never going to scare. So it has to heal by itself. It has to support organic growth. The growth, you just plug in a new rack of machines, the storage, not just the storage, given that all of them are software stack. Your compute as well as your network bandwidth, everything grows with it. Ability to work with disparate performing hardware systems. This is very similar to what we saw. I mean, there is no single vendor in your data center anymore. There is no preferred vendor. You just go get any system, that meets your spec, and then you just your software stack should make it work. And this really helps in controlling cost. And another aspect to it is not just a single spec, but as you go down the line, 12 months 18 months down the line, your data center will not be a single spec. There will be varied vendors. There will be various performing spec nodes in your system. So, but still your software stack has to balance these differing performing nodes in your network and manage performance. And a seamless integration with the provisioning, securing, and management. So administrators pain has to be, is pain number one. They are the ones, and it's really, if you go to any deployment center, it's one of the biggest pain points that needs to be addressed. So we had a lengthy discussion, but supposing I have I'm a typical storage vendor, right? I make a SAN controller or a NAS controller. So if I pick them, right, and then go under OpenStack virtualized environment, and then write a Swift or a Cinder plugin, and now on top of an OpenStack, if you're a customer, you will be virtualizing storage, you will be virtualizing compute, you will be virtualizing your network. But behind you are using your traditional still SAN controller. Is it really software defined storage? Is this what it is? Let's see what SDS is defined by SNIA. Both the data part and the control part needs to be virtualized. This is understood. Storage service interface needs to allow data owners to express requirements and service level agreements. So there is two ends to it. So there has to be a service interface where there are two people involved here. One is a deployer and one is a customer. So the deployer is the one who sets up the infrastructure. He is going to set bare minimal infrastructure constraints, and there is somebody who's signing up service level agreements, and then they make a contract saying, okay, this infrastructure has to support this level of agreement, and then there has to be a binding of that agreement to typical resources. to guarantee that that kind of agreement is maintained by your infrastructure, and it has to provide that kind of an interface. And SDS should typically include the following functionality to claim the title, right? It has to support automation. Automation means simplified management interface. And a SAN or a storage, by itself has been supporting something called SIMOM, SMIS. Those are typical, standard, I would say, interfaces, methods to control your storage. And but we are moving on to not just traditional block and file, but we have something new called as an object store in today's world. Standard interfaces for a management, normally all of them, these vendors will come up with their own, and that's where I said SMIS, and this is one of the standards to control them. But traditionally, not traditionally, but today we are looking at a different kind of an environment where there is an API contract that is traditionally exposed over HTTP REST interfaces that is gaining prevalence. And virtualized data path, so it is virtualized not just for block and file, as we know, it has to also support object interfaces and scale, and it has to support scaling without disruption to availability, reliability, and performance. If you look at these four aspects, right, there is nowhere it mentions anything about your solution being on a proprietary vendor systems, right? So even your traditional SAN controller that goes and provides these kind of an interface can be claimed SDS per SNIA. But the market by itself doesn't view it this way. SDS typically to deployers and consumers, this is how it typically looks like. Somebody looking at as an SDS from a consumer point of view, I see, hey, for a block level, there is Elastic Block Store from Amazon, and there is a Google Compute's block storage as well. And then there is this Ceph RBD, Radar's block device from Ceph. And SDS on a network file. This NFS and SMB are typically storage I will say protocols on the wire to access your storage, and these are two standards. And it doesn't matter, any storage silo needs to support that. So typically no change on that from SDS. And distributed file storage. This is something which used to be, which people think it's something new today, but this has been in picture for a long time, part of a very niche community called high performance computing. There is a GPFS from IBM and Lustre open source solution again, which predominantly enable you to actually have your storage scale across, scale out in your environment. And this has been traditionally part of your HPC environments, right? But what changed? It all changed, as I feel it. It changed around 2003-4 when Google came out and published their Google File System. And Google File System laid the foundation for a greater trust and innovation happening in distributed file storage as I see it today. HDFS came in as a first step in lines of how Google File System was done. Then today we have GlusterFS, Sheepdogs, FFS, all these providing distributed file storage. Each of them, most of them I would say are open source solutions and quite stable as well. And there is a newer form of storage that I see more prevalence today is the object store. And object store is typically useful when you look at, today a prevalent of applications do create once but consume many times. If you have heard of warm IO profiles, write once, read many. Think about your pictures. You take pictures from your mobile phone, from your cameras, and push them. Think about videos. They are created once, pushed to YouTube, right, and then consumed many times over and over. So it's an object binding and with some metadata, and most of them fall under write once, read many kind of an IO profile. And we see Ceph, Rados, AWS S3, OpenStack Swift, or some of the solutions out there that is providing object. And in this discussion going forward, I would base most of my discussion over SIF to highlight how SDS and open software-defined storage by SIF is helping out address many of the problems that we have highlighted earlier. So what it is, so we just talked about SDS, how it is to consumers, and how it is likely to look tomorrow. So block and network shares, as we have known traditional, will continue to exist. That is how there are tons of applications already built over this interface. It cannot go away. So thinking that it's all distributed and a new kind of interface is really, in my opinion, not going to go really well. So you will have to carry your existing solutions, provide block and network shares, and going forward, all your storage systems from a consumer point of view would be a unified distributed storage that supports logs, files, and objects, and it's going to be a must requirement. And since the worm IO profiles are providing everywhere, and that is the driving the object store, and newer frameworks are emerging that will take computation close to data. See, this I believe, as I entered, Google file system came up with GFS, or distributed file storage, and then on top of it came HDFS, and then HDFS is just the groundwork. The core of it is, if you look at Hadoop, it covers two aspects: a compute framework as well as a storage framework. The compute framework has got something called as a mapped reduce. So typically we are looking at, the problem set, how we would traditionally do compute on some task is, given the scale, you have a DB, you pull all the data from the DB, try to crunch them, and then come at a conclusive solution. This is how a typical workflow would look like. But given the scale, again, this is a never-ending repeating. I'm going to repeat this till it gets sunk in everyone. The scale of the data is huge. It's humongous. So bringing all the data to your compute node and then computing, it's first thing, it's never going to fit. And if you're going to bring in the data is going to be there forever. So if you're doing some real-time computation, probably it won't be real-time anymore, given the latency you would have in not just pulling your data but computing what you need, your needed result. So the strategy was, given that data is everywhere because it's a distributed file, you just relocate your compute logic to all those nodes, and each of those nodes only pick data that it can chew, right? So that aspect of keeping the data available on all the nodes is where HDFS, the storage layer, came in. It made your distributing logic to any of the nodes easier, without any. So that the binding of logic and data was separate now, has been separated, because you have a fluid storage layer that allows your data to be accessed on any node. Okay, so it doesn't matter where your logic runs, you will always have access to data. So that's what HDFS and GFS brought into the table. Then the second one was, your problem can now be, you have a simple logic, what you want to do, and then you split this logic and then send this logic, distribute this logic to n number of nodes in your cluster. And each of those logic now, instead of data being pulled from remote, you have logic being pushed to it, and with the logic and a limited set of data that it could chew, it computes the relevant information. So you see that, and then there is a remap phase. It's a reduce phase, which is well known as a reduce phase. You take all the results, computed results, and only get the relevant, extract out the relevant information just out of that summary to get your results. So you see that this what HDFS or GFS has brought into the table with this fluid storage. You could see your problems in a different scale now, right? So even though your data is getting exploded at a humongous rate, you could write logic in a way that you distribute your logic to run on separate nodes, and then you collect the summaries and then make your result. So the idea these frameworks are bringing into the table is making it easier to split your logic to different nodes, and the data is always available because it's a fluid storage. So that's the kind of things that you are going to look at, like more and more and more frameworks are going to come on top of this fluid storage environment. Already we have seen on top of HDFS there is so many, Kafka, there is Storm, there is Spark, whatnot. All of them are based on the similar principles. So we looked at, coming back, some of the plaguing problems and how SDS does really solve them, right? So let's look at a few aspects of SDS that, I think is relevant for a discussion today. So we talked about data placement. So earlier, you could just have control over, RAID 5, RAID 6, right? That's about it. You have a bunch of drives and it knows how to manage. Now you have no control on how to distribute. Say supposing you have a rack of SSD drives and another rack of your platter mechanical drives, and you want replicas to be distributed that way. One replica goes to SSD rack, the other one goes to your mechanical rack. Right? These kind of logic are hard coded in your, even if it suppose it's hard coded, it's not flexible, it's not amenable, right? So now what does this SDS? So I'm going to highlight this with an example of Ceph. Ceph is an open source storage stack, and it's a unique concept called crush maps. What is crush? The crush is a logic. It's a logic how to distribute data in your cluster. So its crush stands for controlled, scalable, decentralized placement of replicated data. So what it is, let's take a look. Given buzzwords are always there. So it allows an administrator, through crush map to define their own physical hierarchy. Your data center will have, it's never going to be fixed. Given how it's going to scale, the hierarchy is never going to be fixed. There is always going to be change. There are always going to be new nodes coming in, nodes going out. But this hierarchy has to be somehow captured so that your storage layer is intelligent to distribute and replicate data in a way that I want it, right? So you could define your own hierarchy. In this example, as I see, I have a 3-layer tree. The root rack bucket holds 2 host buckets, and every host has got 2 OSDs. By OSDs are typically equivalent to your drives, disk drives. Right, if you look at on the right hand side, you could see that I define 2 host nodes, and there is a rack, and this is how you go ahead and define your you could see on the host node there are 2 items, 0 and 1, so it holds 2 drives. There is a weight, and there is a rack on top that holds these 2 nodes as its elements. This way you could capture a hierarchy. So once you have captured your hierarchy, so I would want to show, right, so now what are the other things? How would you place items into your environment? So you could write rules, and you could set your rule to your pool. So here you say minimum size, maximum size, and here is a logic you write that is based on your environment to know how to actually assign a rule to your pool. So this way, if you look, just to illustrate here, step take SSD. So if you're saying you apply this primary SSD primary rule to a pool, and you write an object to this pool, it's going to go run through this rule set to actually figure out the drives on which this object needs to be set up. So it is not going to give out a single drive, it is going to give a list of drives. And supposing your pool has been set for, say, 3 replicas, it is going to choose the first 3 drives and then push your objects there. Right, and if you look at this rule, it says step take SSD. So it takes the SSD root and then choose 1 drive out of it. The step emit says choose 1, and then they take the platter hierarchy and then choose the rest from it and enter. So you have if you set up your pool for, say, as to illustrate, 3 replicas, what it's going to do is it's going to choose 1 drive from your SSD root and 2 drives from your platter, which is your mechanical drives, and then complete your replica. So this is how typically you have more control over data placement. right? So let me move on. So the other thing is replication and erasure coding, right? So replicate we saw just now, take a data and traditionally, you just write, same copies n number of times is plain replication. But replication has got a side effect. Even though it's simple, the data growth, if you have a replication of count of 3, it's going to grow 3 times. Whereas with erasure coding, what would happen is it typically grows, 1.5 times x. Not at the not you don't you're not really writing the same data as a whole, but what you would be doing is you would be having a logic to actually write partial content. I would say magic data that will help you retrieve in if there is a failure. Erasure coding has been known since long, but you would have heard only about RAID protocol being predominantly used with storage, SAN environment, RAID 5, RAID 6. RAID 5, RAID 6 can be mapped back to erasure coding. But erasure coding, even though it was discovered earlier and is well known in the academic industry, it went on to have more say in communications, because you send your packets over the network channel, communication channel, which is always noisy, not guaranteed to be sending, the receivers receive the same data, where it's not just that you lose data, but the data by itself could change on the wire. But traditionally with disk systems, what you would see is you would either get the data or the data would fail. There is no in-between state where the drive is up and you read and you get invalid data, right? I believe you would appreciate the difference there. But let's go on to see what erasure coding is all about, because that's the buzzword these days. So if I have K data disk, right? So typically, sorry. So if I have K data disk and M coding disk, so this is think of it, if people coming from the storage domain can look at it from a RAID perspective as well. You have K data disk and your coding disk is where you hold your parity, right? For RAID 5 you have a XOR parity, and RAID 6 you have two different Galois field logic. One would still be the parity, but the other one will be a different equation. Just stick on to that. Even RAID 6 comes from erasure coding for that matter. So these M coding disks are going to hold some magic data. If RAID 5 is a parity, right? So some magic data. So if one of these data disks were to fail, it can read that magic data and recover the data that was in this particular failed drive, right? And for those K data disks, you are going to write M coding disk, and typically this is the kind of linear equations, that going back to your academics, linear equations would involve solving matrix multiplication and inversion. You could come out with any coefficients A0, 0, 1 for them, and D zeros that you typically see are the data that goes to your data drives, and then you could come up with any equation. The only condition is it cannot be concurrent. I don't know how many of you still remember concurrency means if multiple lines, think of a line, and if you just multiply a line with an integer, you get a different equation, but they still represent the same line, right? So concurrency would actually, even though you seem to have n number of equations, you would degenerate to having lesser than n. So your equations shouldn't be concurrent. And the other aspect to know is there is something called as MDS, maximum distance separable. So the whole aspect of having M coding disk is, if there is a drive failure, the drive failure, you should ideally support M drive failures, right? Assume M ideally would be only less than K data drives. You are not going to have your magic drives more than your data drives. That doesn't make sense. So if you have M coding disk, then you should ideally support M data disk failure, right? If it supports less, then your equations that you have come up with are not optimal. It is not maximum distance separable. As simple as that. Now, I said you could have any equations as long as it ensures that your solutions are optimal, right? But but you will have to compute them, right? Performance is a criteria. So you have to ensure that these equations are easily performable with less compute cycles. So there is a field of there is a separate field that lets you actually control how you can define these equations, and that is called as a Galois field. The Galois field will let you how you can actually compute this whole magic easily, right? And you will have to define your multiplication and addition over this over the data bit and in these equations. So if you could plug in and then solve these equations, there you have a set of n equations and m coding disk. And if you typically take this the one of your coding disk to be, if C0 is going to be your XOR parity, that's RAID 5. C1 is going to be a different some other equation, then you will have your RAID 6. Right? So you could that is how typically it's done. So the basis is, remember, it has to be optimal, your linear equations, such that your M coding disk would allow you to sustain M failures, which is it is maximum distance separable. So how does in Ceph, again, there are disparate systems. I said over a period of time your data center is going to support different vendors. How is it going to be managed? So you have a concept of associating weight to the performance capability of your drives. So when you do that, this information is captured by the crush magic. When you define your nodes and hierarchy, you will have to necessarily specify the weight of the drive in your nodes, and this information will be fetched, and then whenever the data is being distributed, it will be distributed based on the performance capability of your drive, right? So this will in turn, that is how SDS does support disparate systems and keeping your performance on par. Again, failure healing. What Chef does internally is, given that there is this whole pool of disk cluster, which is OSDs, they all form a group. They form a peering group. Of course, there are some conditions which I'm not going into deep there. They all send a peering group and then are in constant touch. They send hello packets, and if there is a drive failure, immediately that pool knows, oh, okay, there is a disk failure, and whatever data that goes into the drive can be computed by the rest of them, and then they manage moving those data, because there is a replica in place, right? So from other OSDs that has the data, the data is replaced and shuffled, and then the cluster comes back again healthy, even though there is a drive failure. So without any external involvement there. So these are some of the aspects that I would want to highlight, right? So that is how SDS has come in to help, which is definitely needed in terms of addressing some of the play points we have highlighted earlier. Now, having said that, is SDS the panacea of all things you see? And again, this again comes from, I just want to highlight, I don't want to just give you some presentation or a talk that you listen and forget. This is a live deployment. Last year it was conducted, and again I feel it very, very relevant to bring it up here again. Which of the following surprises did you encounter after virtualizing your application? So you had your environment and you said, hey, SDS is all hunky-dory, let's go there, and it will solve all my problems. No, people did deploy and move into SDS and then came out with different problems that they still struggle. We said capacity planning. Remember, we started saying capacity planning is outdated, and people end up saying determining requirements became more difficult even after moving to SDS. So there is still some more work that needs to be done. Response was slower, so applications became slower, and given that this is a cluster, SDS is a cluster. Your data lives in the cluster. It is accessible anywhere, but still some applications don't work. Your cluster doesn't come up. Need a dedicated shared storage to bring it up, and there are failures that cause total outage. right? So I mean, if you look back and think for a moment that it really did solve most of the problems, but the problems are still there because SDS, if you think about it by itself, it's a complex software stack, and then you will have to have train your administrators to go through a learning phase to understand what it is. It's an innovative concept, and people are trying to catch up. To control cost is one thing, but also making your administrator conversant with understanding how to bring up and keep your system and a cluster available anytime needs a lot of work. So the problems are still there in one form or the other. I mean, it might have gotten better in few of your access, your cost you could control, some of the issues is easier to handle, but still some of the pain points are still there. So it is still early days for SDS is as I see it. What are the typical problems? Performance problems was highlighted, but what was it really? The slow applications. It's mostly applications that were developed without concern on what particular infrastructure it's going to be deployed. So what it really hints at is application developers need to be more aware of how their applications needs to be designed, because performance is not just an infrastructure problem, it is starting right from the architect and design stage of your application. So slow applications was a predominant primary reason for having performance problems. The other aspects is still part of the problem. We talked about SDS being, all plurality, embracing, different things, but still legacy storage, incompatible drives do exist and cause performance issues. So again, coming back, one other aspect, you had data center outage. Nope, that's a big no, but still you had it. So what was it? What was the primary reason? I wouldn't be surprised looking at it. Human error is at 61%. So moving on from your earlier deployment to SDS doesn't really address one key area, human error. So it is a complex stack. It is making it even more challenging. The thought process is all different now with SDS, and human error is definitely going to play a big role. So there is always scope for improvement in your SDS stack as well. So that was a big discussion. So given that context, I would want to conclude with what does SDS really does today. SDS does help in moving with isolated storage. It's just not anymore storage silos, but with converged and hyper converged and virtualization on top of it, it allows storage to be available anywhere. The storage controller which was dedicated is no longer there. Your hardware cost has come down, and the services that actually manage your storage is being run alongside with other applications. The intelligence for managing your store data has moved from your dedicated hardware systems, proprietary solutions, to purely distributed solutions. And most of them, I should highlight here, are open source technologies. And this is one key factor as well. And the technology and the industry that people wants to deploy, they wants to deploy mature solutions, and open source solutions are maturing faster because there's a large community drive around it, but support is always a problem. So that is where proprietary companies could come in and really help out supporting. Red Hat is one big thing there which supports many open source technologies. So mostly we are moving away from, the point I want to highlight is proprietary solutions to open source technologies in this space. So AWS, GCE, and likewise rules infrastructure and SDS as a role. I mean, it is the fundamental there behind the scene that is making it all work. And SDS is laying the path for bringing innovative ideas faster to deployment by being largely hardware agnostic. So think about it. Can Hadoop, Storm, Spark frameworks exist without GFS or HDFS underneath? And that is a big win for all of us. So SDS is really going to have a great say here, and these are the references. So most of my SDS has been based on Ceph stack, just to highlight where we are, how it supports various features, and the marketing material I took. The poll that happened was from Data Core. That was last year, but the contents were very relevant here as I see it. And if you want to read more on erasure coding, there is a very nice paper there, and the image sources are all Google. So that's the presentation as is, and there is a poll to go by. So I hope you spend some time responding to those polls, and I hope this webinar was useful to you and you had a good time over here. Thank you.